Log on, tune in, find out. Another good idea from Cambridge.
All right, so this is the plan for today. And the leitmotif so far of these lectures was the connection between those two things on top, which is complete moduli of stable pairs, higher dimensional analog of MG and bar, and birational geometry. And what I will try to explain today, I will try to add the GIT to the picture and explain, complete that triangle. And let me begin with the Grassmannian. So a Grassmannian GRN, that will be the Grassmannian of r-dimensional subspaces in a fixed n-dimensional space. Then on this n-dimensional space, we have a natural action of C star to the n. And the diagonal C star sends every vector space to itself. So that's the action. So therefore, if I consider the torus, which is that C star to the n modulo the diagonal C star, then we have a natural action on the Grassmannian. Okay, so that's the setup. Now we have a fixed Cn. Let's projectivize it. So we have a Pn minus 1. And inside, there is the projectivization of this V. That's isomorphic to Pr minus 1. And so this guy is fixed, and that's a subspace we vary. And on this fixed Pn minus 1, there are n hyperplanes. Hyperplanes Hi, right, on Pn minus 1. So now if you consider this vector space inside, this PV, then the intersections BI, HI intersect PV, they will give you hyperplanes on PV. And so therefore, that's your hyperplane arrangement, this PV and this sum of BIs, and we will consider them with the coefficients. But that's where they come from. Now, if PR minus 1 and the sum of BI is a generic hyperplane arrangement, so in general position, then such a thing is exactly the same as a T orbit in the Grassmannian. So you have an action of this torus, and of course this action sends a hyperplane arrangement to an isomorphic hyperplane arrangement, and I'm saying that's it. So for a generic hyperplane arrangement, this T orbit gives you this hyperplane arrangement. Now let's add the moment map and the polytopes to the picture, because I'm going to use the stable toric varieties. So there have to be some polytopes in the picture. Here's how they appear. The Grassmannian, there is we will consider the Plucker embedding. So it's an embedding into P, into this projective space. And then the torus acts here. The torus also acts here because it acts on that Cn. So we have a moment map. The moment map mu, it sends the Grassmannian to a polytop. So mu sends to a polytop. The polytop sits, it's called delta Rn. So the hypersimplex. And it sits in Rn minus 1. The vertices of this hypersimplex, they just correspond to Plucker coordinates. So there are n choose r vertices. Another way of describing this polytope is by inequalities. And they will look very similar to what we had yesterday. That's how you describe it by equations. So if you recall, yesterday there was some chamber D, and there was a chamber decomposition. And in this chamber decomposition, there was this lower face whose points corresponded to GIT quotients of the Grassmannian. That lower face is precisely delta Rn. So that's what it is. It has n choose r vertices. The vertices have coordinates r1s and n minus r0s. Now suppose you pick a point in here. So a point is it's a vector space like this. Then you can act by the torus on this orbit, and you can close it. And this closure turns out to be that this is a normal toric variety. So, and it corresponds to a polytope. So the moment polytope of that variety, it sits in here, and this is called a metroid polytope. So this is what the metroid polytopes are, as defined in in these terms, in terms of symplectic geometry. You take an orbit in the Grassmannian, close this toric variety, look at the moment map, look at the moment polytope. So there is some subpolytope here. There is a nice combinatorial theory of these metroid polytopes. They can be described again either by their vertices or by inequalities. So both are nice. They are nice polytopes in the sense that they are generating unimodular, nice things. Now, let me give the first indication of this connection between birational geometry and GIT by stating another definition, or it's like a lemma. But it's another definition of this metroid polytope. So we'll call it PV. It depends on V. Here's the lemma, that PV is precisely the set of BIs such that sum of BIs equals R that we had. And the pair PR minus 1, sum of BI, this pair is log canonical. So turns out the proof is just, this is a condition which I wrote down yesterday. And you look at the definition of this metroid polytope, and you see that they're the same. So that gives you already an indication that there is some interesting connection between GIT and these log canonical singularities. Now, let me also say that when you start with a generic orbit, then this metroid polytope is the whole thing, is the whole hypersimplex. And indeed, if it's a generic hyperplane arrangement like this, then you can put any weights between 0 and 1. That's log canonical, because you have normal crossing divisors. And so all possible BIs are in your polytope. But if your hyperplane arrangement is not generic, maybe something like this, then only for some BIs you have log canonical. So you have a smaller polytope. So you get this metroid polytope. Okay. So that's the setup for the Grassmannian. Now, what I want to do now is I want to describe the variation of the GIT problem for the universal family over the Grassmannian. So the universal family sits over the Grassmannian, and it's a subset in the Grassmannian times Pn minus 1. So we vary this subset of Pn minus 1. That's the universal family. And the torus still acts here. Now, I would like to consider this VGIT for this universal family. GIT problem, the GIT problem. In the GIT setup, there are two things to define. First, you have to define an ample line bundle. And secondly, you have to define a linearization, or L, a linearization of T action on L. Now, here's the statement, and this is somehow it's the heart of the whole matter. Yesterday there was this chamber. I defined the chamber D, and it was those BIs which are between 0 and 1, and where the sum of BI is greater or equal than R. So that was the chamber. And then there was some chamber decomposition coming from somewhere. So here's the point. A point, an element of this chamber decomposition is in a bijection with data like this. That's my statement. So let me tell you how. The ample line bundle, given a beta, this point beta, so that's B1 through Bn. Given a point beta, first of all, I need to define an ample line bundle on here. And I start with the standard Plucker bundle on the Grassmannian, and then I need to define some line bundle on this Pn minus 1. And by definition, this is what I do. So I just sum of BIs minus R. And so this ample line bundle, it corresponds to a horizontal line like this. We just fix the sum of BIs. That's what this ample line bundle, the choice is. The choice of an ample line bundle is a parallel hyperplane in this direction. Now, what about the linearization? Well, the linearization is precisely the same as a line through the origin. So that's linearization. That's how it is. So it kind of, from the definitions of GIT, that's an obvious thing for the torus. So in the intersection, that gives you this beta. So this beta is those two things. That's what they are. Now, GIT, there is VGIT, so variation of GIT. So you change your data for the GIT, and your GIT quotients change. And that always gives a chamber decomposition in the setup of GIT. And if you're in the same chamber, then your GIT quotient is the same. And then as you cross a wall, then the GIT quotient changes. So for this U, one has to compute this chamber decomposition. And let me just tell you the answer. The answer is precisely that chamber decomposition that I defined last time. So that's what it is. It's given by the hyperplane where some of the weights add up to k. So k is between 1 and r minus 1. So that's the explanation. Okay. Yeah, let's look at this case. So what happens if the sum of equals r? That means this projective space just disappears. And what's left is only the Grassmannian. And when you take a quotient, you're just taking quotient of a Grassmannian. And so that agrees with what I explained last time, that the points alpha on this lower boundary, they just correspond to quotients of the Grassmannian itself. And points which are higher, which are in the interior, above this face, they actually correspond to GIT quotients, no longer of G, but really of U. Okay. So now I'm going to say again?
Why the condition that the sum of the BI equal R for this PD?
So the hyperplane where sum of BI's equals R, that's precisely the lower face of the chamber. Is that clear? So that subset is given by precisely these two conditions. BI's are still between 0 and 1, and sum of BI's equals R. And so that's our hypersimplex. So this part. Okay. So here is the second connection, which is a lot deeper than this lemma. So I'll call it a theorem. So I'd like to know if now I take a point not in the Grassmannian, but really on the universal family. So a point on the universal family, that means first I have a point in the Grassmannian. So I have PV in Pn minus 1. But now I also take a point in here. And then I claim that it is GIT semi-stable with respect to beta. So beta gives me this GIT setup. So there are semi-stable points, there are stable points. So that implies that the hyperplane arrangement PR minus 1 sum of BI is log canonical at the point P. And so theorem, easy to prove. The way you prove it, the semi-stability condition is there is the Hilbert-Mumford criterion that you have to check. For tori, Hilbert-Mumford criterion is the simplest thing imaginable. Really, you just check whether some point is in some polytope, and you see that this is easily implied. But somehow that's the connection, and that will imply that our stable weighted hyperplane arrangements have semi-log canonical singularities. So it's almost if and only if. There is some obvious necessary condition that has to be satisfied. Let me say this. So take a point in this projective space which is outside of the hyperplanes. Okay? Then clearly, at a non-singular point with no hyperplanes, you have log canonical. But the corresponding point could be, it's possible that it's not semi-stable. Yeah, that happens. On P1, a simple example on P1. But if ignoring this kind of obvious necessary condition, I think it's true. And I actually spent a long time trying to prove that it's true. And I could prove it for R equals 2 and 3, and I really don't need it, so I decided I'm not going to spend any more time. It's probably true. Okay, so number 2. I'm going to define the weighted hyperplane arrangements for you and their moduli spaces. And I will start with the moduli space. So there is this moduli space for of these hyperplane arrangements. And the first definition will be for the weights 1, 1, 1, 1, 1, 1, 1, all ones. Here's what it is, by definition. It's the moduli of stable toric varieties y over the Grassmannian. As definition, the definition. And then if you consider with the weight beta Rn, then again it's the moduli of stable toric varieties y over some new variety, which I call a weighted Grassmannian. And this has nothing to do with weighted Grassmannians of Reed and Corti, but yeah, everything is weighted here, so I couldn't think of a better word. Let me know if you can think of some. So there is some version of a Grassmannian that appears here. That corresponds to this weight beta. So you can look at this. All right, and let me define the weighted hyperplane arrangement. So here's how it works. So you have y, and y maps to the Grassmannian. And remember, this is a finite map. And then over the Grassmannian, you have this universal family. And then you can look at the fiber product. So u times y over g. And then you can take this u cross y over g. There is the torus acts on it. And just divide, take the GIT quotient of that with respect to this choice beta. And that, by definition, that is my x. And now u lives in the Grassmannian times Pn minus 1. So it comes, this u comes with n hyperplanes. So this x comes with n hyperplanes. And that's it. That's my definition. And so looking at this, the immediate question is, why in the world, right? What does this has to do with anything? Kind of looks tricky. But let's do the following. Let's consider the special case when this PV in Pn minus 1 is generic. So you have a hyperplane arrangement in a general position. Now, in this case, this remark applies. That generic hyperplane arrangement is precisely the same as a torus orbit in the Grassmannian. So there is this, the Grassmannian, and inside there is this torus orbit, this T, and this Y is the closure of it. So the closure of it. Now let's ignore the difference between stable and semi-stable, and the way not to ignore it is to consider a little b prime, which is b minus epsilon, and look at b prime semi-stability, which will be the same as b prime stability. But let's ignore this little detail. So let's not look at the boundary. Let's just look at this torus orbit itself. So what am I doing here? That's my y. That's this y. This is the closure of this torus. Now, over it, I'm looking at the universal family. So over every point, I have a hyperplane arrangement. And it's a t-orbit. So t-orbit. So all these hyperplane arrangements are isomorphic to each other, right? It's a group action. So all these points in the Grassmannian correspond to isomorphic, to the same isomorphism class, to the same generic hyperplane arrangement. And I have a torus action which is free. So when I divide this by the torus action, what do I get? I just get this hyperplane arrangement and nothing else. I just get that hyperplane arrangement itself. So that's it. So for a generic hyperplane arrangement, when this y is just a toric variety, a closure of a unique orbit, this definition actually produces this hyperplane arrangement back to you. That's for generic y. And then for non-generic y, then this y now becomes singular. It splits up. Instead of one toric variety, that toric variety degenerated. And now I have a stable toric variety. And so now something, I have something non-trivial. So now let me.
Again, the picture where it breaks.
So I have a family kind of these toric varieties. And eventually it breaks. It's, remember.
So like in these pieces there,
It's so you have a conic, and these are toric varieties, conics, and then it splits.
So like in the locus where it splits,
Uh-huh.
look at the actual hyperplane arrangement in one of the
Oh,
parts
so
and one.
hyperplane arrangements are in the fibers over this.
Yeah.
This
so
is in the
fiber
Grassmannian.
over a point and the left
Over that point, the fiber will be kind of some special hyperplane arrangement, very non-generic.
And they're non-generic on the two sides also.
Yes, all of these will be non-generic. That's
But,
right.
like, all the ones on the one piece will be isomorphic. Will be the
That's
same.
right. All the hyperplane arrangements here will be isomorphic. That's right. And then there will be this, and then there will be those, and then there will be that. What's the difference between these are non-generic, but they are somewhat generic, right? Somehow feel better. They're better than this one. The difference, let me just say, the difference is that for these hyperplane arrangements, the automorphism group of the pair PR-1 plus those hyperplanes, that automorphism group is finite. And so the torus orbit in the Grassmannian is of maximal dimension. And the automorphism group here jumps. And so the torus orbit becomes smaller. That's the difference.
And
But
also the points on the ends.
right. So all of these are special. And here also the orbit is smaller, the automorphism group is bigger. Okay, so now I would like to explain why that's defined X, why this hyperplane arrangement has stable, has semi-log canonical singularities. Why is it a stable pair? Now it's almost, we're almost there. I'm just going to add 1 plus 1. First, the stable toric variety has SLC singularities, right? That was the main idea on Tuesday. So these stable toric varieties are the easiest SLC singularities. And every fiber, that's my theorem over there. Every fiber with these weights, BI, precisely with these weights, BI, that's log canonical. So every fiber is log canonical. So you have, it's like almost like a Cartesian product. It's not, but let's pretend that it's a Cartesian product. The base is SLC, and the fiber is log-canonical. So then the Cartesian product is SLC. So it's there is no such argument in general, but here it's such a simple situation, I can just give an explicit resolution of singularities and see that this variety is SLC. So that's the point. That's how, that's why. That's why these pairs have nice singularities precisely for the BIs. It's because of this connection with GIT. So that's that side. All right, and K plus B, why is K plus B ample? Now, GIT construction always gives you an ample line bundle on the quotient. That's the essence of it. There is construction, you look at the ring of invariants and you take its proj, and on this proj you have an ample line bundle, just coming from GIT. And you compute this line bundle here, and it's K plus B. So GIT tells you it's ample. That's it. That's the proof. So that's how. And let me show you some explicit computations with this. So now, yeah, how do I compute these moduli spaces? Well, I have to compute these stable toric varieties, so computations. And so I start with delta Rn. This is this hypersimplex. And for a generic hyperplane arrangement, this moment polytope is just the whole thing, is this polytope. And then when it degenerates, when it splits up, this toric variety splits up into several toric varieties. So this big polytope splits up into several polytopes. Now these polytopes, they still correspond to orbits in the Grassmannian. So therefore, there are these metroid polytopes. So every degeneration, every stable toric variety, that's what it's described by. It's described by a tiling, a subdivision of this big polytope into metroid polytopes. Now, metroid polytopes, as I said, they are very special polytopes, but now this is what you have to do. To describe a stable toric variety, it's just you have to describe all the ways how this delta Rn can be split into a union of metroid polytopes. It's a finite question. For low R and N, you can do it by hands. I'll show you some answers. For big R and N, maybe you can use a computer. In any case, it's a finite, solvable problem. I suspect it's NP-complete. But for big N, it's an impossibly long computation. But for low R and N, this is actually doable frequently just by hands. Now, how does beta appear here? So I mentioned cryptically that there is something called this weighted Grassmannian. So what is it? So here's what it is. So delta Rn, let me write one more time the definition. So each BI has to be between 0 and 1, and sum of BIs has to be R. And now I will define delta beta Rn. And that's the same thing, but, bad choice. So these are X, and each x, sum of x's. Because now that's what I want to do. Just instead of looking at this big thing, just look at the small. So you get a small subpolytope here. So that this polytope is delta beta r. So the point is that when you look at the beta semi-stable points, those points only live over the orbits that are here. They only live over those linear spaces, those points in the Grassmannian that correspond to these polytopes that intersect this delta beta. So when you work with the coefficient beta, that's unimportant. That part is just unimportant. You only care how this little polytope is subdivided. And the extreme case of that is when you look at the generic alpha. Generic alpha was, it was a point in here, and it lied outside of all of these hyperplanes. And then if you look at a little polytope around it, it just doesn't see anything. It's not subdivided. So it just sees one polytope that contains it and nothing else. So to compute something explicitly, some stable toric variety and some weighted hyperplane arrangement, this is what I have to do. I have to describe for the weight 111. So this is for the weight 111. I have to start with that polytope and describe all the ways how it can be covered by metroid polytopes. For each such covering, every covering like this describes a stable toric variety. If I have 3 polytopes, that means the stable toric variety has 3 irreducible components. It's just, this variety is just, it's on the picture. It's a union of toric varieties. These toric varieties correspond to these polytopes. And if I'm working with a smaller beta, then I'm only looking at this part. And again, this describes me a toric variety. So those small polytopes, each of them corresponds to a toric variety. And so in this case, that stable toric variety with the weight, it will have 2 irreducible components. Then what do? I look at the universal family, but it's a smooth, nice universal family, right? The fibers are just projective spaces. And then I take a quotient. So if I had 2 irreducible components, after this procedure, I still have 2 irreducible components. And they intersect in exactly the same way. So that picture tells me both how the Y looks, the stable toric variety looks. And it also tells me, more importantly, how the weighted hyperplane arrangement looks. It's just right here. So, if that's my tiling, then it will have 2 irreducible components. So that's the work one has to do. To compute something explicitly. So let me show you some explicit computations. So here's one computation. Let's say I want to compute with the weights 111. I want to compute this. This means I have P2 and 5 lines. Okay. All right. That turns out this is extremely easy. It's just because the Grassmannian G35 is the same as Grassmannian G25. Right? They're isomorphic. So therefore, this is the same as for S25. And here we have P1 and 5 points. And so that's just M0 and bar. So even though these are families of surfaces, they're kind of dual to families of curves. And you can just make all the pictures. You know, a stable curve with 5 points, it splits up in a maximum number, 3 reducible components. And so therefore, these surfaces split up in maximally in 3 reducible components. Maybe I'll make a picture. So if I remember it. So it's 3, 5, 3, 5. Yeah, so you start with the plane, and it splits up either this way or this way, I think. That's all. So these are all the degenerations. This degeneration is a P2 and a blow up of P2 at one point, and this degeneration is a P2 and P2 and P1 cross P1. So now, if you, again, starting with weights 1, 1, 1, if you want to look at P2 and 6 lines, then let me draw some degenerations for you. So P2 can split like this. These are still toric. This is just luck. They don't have to be toric. You know, its y's have to be toric. X don't have to be. And then there is a degeneration like this.
You have 6 lines.
Yeah. So
6 points to the margin 6.
yeah, where are the 6 lines? Is that what you're asking? So I started with a P2 and 6 lines, and then lines degenerate. So I'm starting with P2 and 6 lines on them, and when they're in generic position, they are like this. And then when they're degenerate, for example, here, here's how they degenerate.
I just wonder if the points you marked are lattice points or.
Oh yeah. It's a lattice polytope that I'm. I'm thinking of P2 here as a toric variety. It's P2 with Kp2 plus 6 lines. That's minus 3h plus 6h. That's 3h. So P2 with this ample line bundle as a toric variety, that corresponds to this picture. So that's what it is. And it splits up. It turns out to be, again, a little luck that all of these degenerations are toric. So this big toric variety just splits up into smaller toric variety. But it comes with 6 lines, right? So this is how the 6 lines look in this case. There are 3 irreducible components. Each of these irreducible components is Hirzebruch surface F1, blow up of P2 at one point. And this is how 6 lines lie on them. So these are easiest degenerations, and then you can look at harder ones. Number 3. Now 3, 7. Oh yeah. So those there is a description of all the degenerations here, of all stable toric varieties, and I didn't have to do it because there is a paper of Sturmfels and Speyer on tropical Grassmannians, where what they do, they describe all the matroid subdivisions of delta 3,6. And that paper is not, you can say it's not about algebraic geometry, it's about some tropical geometry. But of course, tropical geometry is just another name for, just another language for describing combinatorially degenerations of algebraic varieties. It just captures the combinatorial part, the discrete part of a degeneration. And so there is a complete list in that paper, so I can just use it. Now for 7 lines on P2, that gets harder and harder. One can do a computer search. But in the application that I will show in a minute, I will need the weights, not 1, 1, 1, but the weights 1 half, 1 half, 1 half. And as I explained, in this case, that means that I'm looking not at the big polytope, but at a small polytope. And I only need subdivisions not of that big polytope whose subdivisions are hard to describe, but only of a small polytope inside with small weights. And turns out that in this case, none of these hyperplanes intersects it. So it's such a lucky case. It's all of these hyperplanes, sides of the Metroid polytopes, they all miss it. So that means that you start with P2 and these 7 lines BI, and you degenerate, and it still stays P2. It does not split up. And you have, again, 7 lines. It's just non-generic. So that means some 2 of them may coincide, and some 4 of them may pass through one point. So non-generic. But it still looks canonical, so these are the worst things that can happen.
But you changed all the weights to 1/2.
Yes. Uh-huh.
I mean, they were 1 before, so if you have
Yeah, it's different. That was number 2, this is number 3.
Yeah, but I mean, is that so that little triangle is small enough?
Yes, that's what it turns out. That with 1/2, this little.
So it wasn't lucky, that's why you made it 1/2.
I needed 1/2 for the application. You will see the application. But this is delta 1/2, 3.7. And so for that application, that's the weights I need. And I was lucky enough that it missed all the hard stuff. Okay, there is one more case. I don't think I'll put it on the board. It will be on in the slides. Now, I want to move on to the last topic, and that's applications to surfaces of general type, to moduli, complete moduli of general type, surfaces of general type. So here's the, first of all, let's begin somewhere. So you start with a connected component in, let's say, an irreducible component in the moduli space of smooth surfaces of general type. And moreover, you even assume that the canonical class is just ample. So that's M. And then, so the idea here that I try to get across is that MMP tells you that there is a compactification M bar. And this is the moduli now of stable SLC KX ample surfaces. And so that was the original idea in this 1989 paper of Kohler and Shepard-Barr when they first thought of this. And so MMP tells you that thing should exist. And then there are many, a situation is hard. You will appreciate how hard it is if you come here tomorrow. I'll try to explain this general case. What we know, what the problems are. There are many things to take care of, but in the end, there is this compactification. It exists theoretically, so it's unlike all of these that case. There's no constructive procedure that you can feed into a computer or something to compute all the degenerations, to describe all the strata. It's kind of a theoretical theorem that there is this compactification. And for the longest time, there were no examples where this M bar would be just explicitly, completely described. There were Okay, there were a few examples. There were examples where you start with product of two curves, okay? A curve of genus G1 and a curve of genus G2. And that's a surface of general type. You degenerate, this becomes a stable curve, that becomes a stable curve, so you have a product. Okay. We'll say that's trivial, okay? So that's not a very interesting example. A more interesting example is you can start with an abelian threefold and look at the theta principally polarized. Look at the theta divisor here. And then there is a theorem of Kohler which says that this surface by itself, if you look at it, it's SLC. And so therefore, now if you degenerate these abelian varieties, there is a complete moduli space which I described, which I tried to explain yesterday. And so you can look at the boundary and check, and turns out that these degenerate theta divisors, they are also SLC. So that gives you an example like this, coming from abelian varieties. And that,
SLC, there's not with the plus B, it's just
without anything, right? So with that was the original sort of settings of Kohler-Shepard-Baron. Also, it turns out to be it's the hardest. So you have K plus B, and it's easy when K plus B is small, when it's an epsilon, almost zero. It has to be positive, but almost zero. But you can only achieve this with coefficient. If it's just K by itself, it's always large, and it's always hard. And so for the longest time, these were the only examples. But now, with these hyperplane arrangements, here's what you can do. You can start with P2 and take a bunch of lines and look at them with coefficient 1/2. And look at, say, 2-to-1 cover. Let's do that. Let's just look at Galois Z2 cover X. And then for the canonical class of Kx, there is a formula, pi. It's very familiar to you Hurwitz formula, just for the ramification, Hurwitz formula for the curves. You just need to see what happens in codimension 1. So this is like for the curves. And this is what it says, that it's just pullback of K of P2 plus 1/2. All these divisors with coefficient 1/2. And moreover, you can check that X is SLC if and only if this pair P2 and sum of BIs with the coefficient 1/2 is, well, LC or SLC, same thing here. Okay? So now, if you degenerate such a thing, this will degenerate to some SLC variety, like in those examples. And cover will degenerate, and it will stay, again, SLC. And for as long as you have more than 6 lines, K plus B will be ample. So it will be a surface of general type. There is B on the bottom, but for this X, there is no B. Okay. Well, so seems like you're close to a win. But remember, I said we, to be honest, we have to start with an irreducible component in the moduli space of surfaces. And if you just do it like this, then this does not give you an irreducible component. Because this you can deform by just smoothing out the union of lines to, say, a curve of degree d, right? Just smooth out. And so therefore, your deformed surface will not be of this type. So one needs somehow some idea that, so what can one do here? And the idea is that something has to distinguish these lines. And they sort of have to have different color. And they should not mix. And so they should be unmixable. So the lines of different colors should not mix. And you can do that if you look not at the Z2 cover, but Z2 to the K cover. So for the abelian covers like this, the ramification divisor, there is the same formula precisely. And there are ramification divisors, but these ramification divisors, there is one divisor for every non-zero element in this group. So the data is just not one divisor, but 2 to the K minus 1 divisors. And so that's the trick. So if you, for example, going to this case, you just look at Z2 to the cube cover, and you need 2 to the 3 minus 1, 7 divisors, 7 lines. And with weights 1/2. So that's precisely this situation. And if you look at the cover like this, they all 7 lines have different label, so they don't mix. And that gives you a connected component, actually, in the moduli space of surfaces of general type. And these are called Campidelli surfaces. That's a very classical. They are Campidelli surfaces. They have k squared equals 1. They have regularity and arithmetic genus 0. These are very old and classical surfaces. And so what this gives you a compactification. In that beautiful non-trivial case, you have a complete answer. And moreover, I can tell you what that complete answer is. It's just it's just GIT quotient for the weight, for the central weight, 1/2, 1/2, 1/2, 1/2, 1/2. It's a smooth variety. Very nice. Now, what I will finish with is a non-trivial, a harder. Yeah. This is non-trivial, I think. It's easy. Again, lucky. But I'll show you another example. If you've seen me present it at some other conference, I'm sorry, it's still the same pictures. I didn't draw. It took me a long time to make these computer pictures, so it's still the same. So I'll, let's see, how does that work, I think? I will use this screen and let's see. And I'm supposed to press the yellow button, right? And anything and nothing happens.
It's not the yellow one.
It's not yellow. Okay. All right. All right. So this is the joint work with Rita Pardini, and it describes you an interesting case of another classical case of surfaces, Bournier surfaces of general type. So what they correspond to this configuration. It's of 9 lines, and 9, that's a lot. So I couldn't, computations here I couldn't do by hands. I used a little computer-aided search. But let me describe the configuration. It's for the group is Z2 squared. And so there are 3 different types. And right now it seems like they may mix, right? They intersect. Maybe you can, those 3 lines, maybe you can deform to a cubic or something. But the construction of Bournier is this. You blow up those 3 points. And now you have a blow up of P2 at 3 points. And your configuration becomes that. And as you can see, the lines or the curves of the same color, they don't intersect. And so this cannot be smoothed out. And so this really gives you a connected component in the moduli space of surfaces of general type. And you can do a Cremona transformation, right? So blow up three curves, and there will be another Bournier configuration. So now I have to apply everything that I described in this case. And therefore, instead of looking at the whole Grassmannian, inside there is a closed subset where the lines are not generic, but intersect like that. It's a smaller subset. It has codimension, I don't remember what, it doesn't matter. But it's a smaller polytope, and I have to describe all the Metroid tilings of that. And again, not of the whole thing, but only that small window corresponding to 1/2, 1/2, 1/2, 1/2. And what I'll do, I'll show you, so there are some mild degenerations when two lines come together, that still look canonical, or four lines go through a point, that still look canonical. And then some serious stuff happens. So this is the first serious case, when three lines try to coincide. That's not look canonical with coefficient 1/2. It's because 3/2 is bigger than 1. And so something has to happen. Let me make a connection with a minimal model program. So I will do a minimal model program for you in this case. So you should imagine a one-dimensional family, and three lines are generic, but then in the limit, they coincide like that. And so you have to find the stable model, then apply MMP to it. So you first blow up that A0, and that's what happens. If P1 cross P1 is embedded, and then you blow up that, that C3, and this is what happens. And then you contract curves, so you get, it turns out, you get now a family and a surface where K plus B is almost ample. It's big enough. And so now you just have to contract the curves on which K plus B is 0. Once you do that, you will get K plus B ample. And so that's what happens. So that's the answer in this case. That's the degeneration. Okay, that was case 1, and then there are more cases. So that's how you compute them all. Or in terms of this, lattice polytopes, you just have to compute the Metroid subdivisions. And then there are, those were toric, so that's really every parallelogram here corresponds to a P1 cross P1, and some triangles correspond to P2s. And this is how the lines on them look. And then there are some non-toric degenerations. So there are 10 cases in all, and that describes all the degenerations. And then, so that's on the bottom. That thing is on the bottom. And then the actual surface, the degenerate Bournier surface, is a Galois cover of that. So you have to see what the Galois cover is. And if you haven't seen this before, it's kind of fun to guess what this cover is. So this surface has 3 irreducible components. Each of them is P1 cross P1. So the cover has 3 irreducible components. And each of those is, can you see that? Each of those surfaces is elliptic curve times elliptic curve. Because you have P1 and you have 4 points of ramification. The cover is an elliptic curve. So there are 3 elliptic curves, and there are 3 surfaces, which are products of those elliptic curves, moduli and involution. And it's a normal crossing. You get normal crossing of 3 bielliptic surfaces. And in this case, you get Enriquez surfaces, for example, or in that case, you get some Delpezza surfaces. So you can compute singularities, lots of things. And this is, again, just for fun, this is remember this line arrangement, it came, there were 2 copies of it related by a Cremona transformation. And so all of these pictures can be approached either from the left or from the right. And that's the Cremona transformation for that degenerate plane. That's the, huh?
Is this a paper available online?
Sure. Yeah, both in color and and black and white version for black and white printers. Yeah. So, and yeah. So, all right, so that's it.